Thank you very much, Chair. And first of all, I would like to thank the organizers. I think this is the fourth talk in QMAT meeting, and thank you very much for inviting me and to present our recent work. So, today's talk is about to understand the magic angle twisted bilayer graphene in using a new measurement technique called the short noise. So, basically I will be focusing two main part, which is the one of the, I would say, lots of debated what going on in the system. One is the superconductivity phase in this magic angle twisted bilayer graphene, and around that is called strange metallic phase, and we are trying to ask question, can short noise can reveal something, you know, which is so far debated, can shed some more light. So, that is the basically outline and my talk. And these are the main students, Soubik, Manos, Ujjwal and Santanu, Sumilon's student who has been working in understanding and theoretical part, and these are people who have done the experiment in this thing. So, just to give a glimpse of twisted bilayer graphene, I think if you have listened my talk, I think first few slides will be same which I have been talking for last few years, and this will be repeating what Rajdeep and Riddhis already yesterday introduced this field. But as the while talking this picture you might have seen, so it's basically two graphene sheet and you give a relative twist angle between them, and that create a Moiré unit cell. You can see the artificial unit cells are created, and the amazing thing is what happens that of course in a reciprocal space also you create a new Brillouin zone, and the most important part is that if you look at the band structure, it's drastically modified than your graphene original band structure we know is like a Dirac dispersions. But here you can see there is a tiny low energy band which is called a flat band created in the systems because of this hybridization between the two layers, and this flat band, and you can see energy is almost independent with the momentum, and energy scale, the width is of the order of few tens of MeV, and that because of that all this interesting physics started appearing. So, just to one important thing which I will ask you to pay attention, that I will be using this called a filling fraction of this Moiré superlattice, which is an integer number -4 to +4. What it says that you have this real space Moiré unit cell, and if to fill the number of electron to the Moiré unit cell you need 4 electron, because here is a spin and valid degrees of freedom, or if you empty this Moiré this band you need to take out the 4 electrons. So, basically from here to here if you go from, you see that this is the flat band and these are the dispersive band. From going from this to this you basically need total 8 electrons in the system, and I will be using these filling fractions throughout my talk. However, this although this theory was proposed long ago 2011, but I think magic happened only 2018 by this Pablo's group, and what they could show that, so this is the exaggerated version of this flat band. You can imagine there is a these are schematic. So, you can see the conduction band, you have a large density of state, valency band, you have a large density of state, and you have a charge integrity point. And what they could show that even if Fermi energy at the middle of your where you have a largest density of state, but when they did the experiment they saw that the conductance goes to 0. So, that is very surprising, right, because you would expect the maximum conductance is proportional to your density of state, but conductance goes to 0, and this is the reason it started all this interesting field that we call this Huff filling, which is a basically in the beginning it was like a Mott insulating peak, but later on in various mechanism and all it basically now we understand is a correlated insulator peak, and it turns out that this you cannot explain by a single particle picture, rather you have to talk about this correlation among the carriers, and this is the correlation physics is very important. So, this is the first important discovery in this field, and of course in the same I think its next volume I guess. Same volume. There is a paper also showing this superconductivity in this system. And just remind you, graphene, such a low electron system, people never have seen any superconductivity, but even in this system the density is still very low, like 10 to the power 11 or maybe hardly 10 to the power 12 per centimeter square, but you still see the superconductivity in this. So, that was the remarkable 2 discoveries, and since then there have been so basically since then what has been done, that there are various techniques has been used to understand. For example, resistance measurement, thermopower, which also we have been doing in our group, then these are all like a global kind of transport, then sort of like a local transport like scanning tunneling microscopy, compressibility measurement, and quantum twisting microscopy. This has revealed, actually it adds more puzzle in the system. And it turns out what we understood that so far, that it's just not only interaction is the only ingredient here, it's also topology is the ingredient, and this together gives you lots of fascinating physics in these systems. So let's that brings it to what I'm going to talk about. So okay, there are many open questions. Of course, as Rajdeep was saying, this is very hard question to answer this. What is the origin of superconductivity? But what is the pairing symmetry of superconductivity? As Rajdeep mentioned, this is a very sharp question, and this should be answered. And there have been various experimental methods to understand what is the pairing symmetry of this superconductivity. And other thing is, what is the charge of this quasi-particle? This Cooper pair, although we feel naively it should be 2e, but there are proposals, it says even 4e. So we don't know what are the charge of these quasi-particles. And most important, which is the main highlight in my talk, will be the linear resistance, what we see in this system, that is the trademark of metallicity. But what happens in the system, this metallicity continues even very low temperature, like down to 40 millikelvin or even below. So that is a very anomalous kind of metal, or called strange metal in the system. And question is, do you understand this system? So that is my our goal, to understand this platform. So let me give you some few slides what is known about the superconductivity in this platform, and where do we stand. So these are the few experiments. Okay, what I am saying is, there are again lots of debate, but these are the claim from these papers. So these are the Nature paper from mostly few of them from Ali Yazdanis and Philip Kim and so. So what they show that when they do the tunneling spectrum of the superconductivity phase, then they don't see this conventional, the hard gap kind of U kind of shape. So that is first anomaly. Rather they see some sort of V shape kind of thing, which the density of state almost increasing linearly. So this is one spectrum, which is sort of like an anomaly. And the second is this Andreev spectroscopy. Andreev spectroscopy is like when the contact is touching your system. It's not in a tunneling regime, but it's a Andreev kind of reflection you have. And it turns out they see this zero bias sort of broad peak. And these two phenomena, it turns out it suggests you cannot explain by BCS, the SOF superconductor. You need to know, you have to go beyond some sort of nodal kind of superconductor has been proposed, and from Rajdeep and Mohit, this Sayog paper talks about, in fact, a very recent paper which he mentioned yesterday, that in fact you can find out what is the pair, whether is a, you can distinguish whether it is a P wave or D wave, which nodal superconductor it is. Yeah, so there is no sort of noise measurement to understand this quasi-particle in this kind of system, and people even believe that even by short noise also you can figure it out some pairing symmetry. Although I will not be going to talk about, we don't see that, but there are theoretical proposals that you probably can figure it out pairing symmetry using the short noise spectrum. So that's about the superconductivity part. The second important part, which I said, that the resistance, the linear resistance. It turns out, so this paper was in 2019. This is the first paper on the linear resistance part. And what they could show that, okay, the resistance, as you can see, they are like linearly increasing at low temperature. However, here the linear resistance happens maybe after, above few Kelvin. And this paper conclude that all these things can be, although, we know the linear resistance curve if your temperature is above the Debye temperature. And it turns out the graphene based system, the Debye temperature is very high. So you cannot have this linear resistance such a low temperature level. But it turns out that in this system, because of the interaction, there are Fermi surfaces malleable, and there are interaction driven phase transition happen, which is called cascaded phase transitions. And as a result, there are tiny Fermi surface, and you can have called Bloch-Bruneian temperature, and one can have the linear resistance. However, these temperature scales are of the order of few Kelvin. So this is the first experiment in this field, and followed by, so this is the experiment even much lower temperature, and they could show that in fact this linear resistance survive in much lower temperature range, and in extra tau this Planckian dissipation rate, and it turns out that they are they can be explained by the strange metallic phase. And I think most promising data from this group, from Dima's group, which they could show this linearity even up to 40 millikelvin, and this experiment was designed very nicely, because you remember in the phase diagram in this magical twisted bilayer graphene, as I told you, half filling there is a correlated insulator peak, and followed by you have this superconductivity. However, here the experiment design was such a way that they can screen this correlated insulator peak by putting a gate very close to your systems, and so they could see this strange metallic phase around the superconductivity in an extended phase diagram. In contrary to the previous paper, the Pablo, there they could show the strange metallicity only around the superconductivity dome, but in this paper they could show even the larger this thing. Okay, so that brings down to what I am going to talk today, how the short noise can shed some light. So since I will be first time talking the short noise here, so let me introduce what short noise, how the short noise was discovered. So this was discovered in 1918 when Schottky was doing the experiment in a vacuum tube, and what he was trying to measure, which is the current coming out in this kind of cathode, when because of this thermonic emission there are occasionally some electrons are coming out, and of course you have a mean current, but if you look at the mean current there are fluctuations. Okay, that is very not surprising, even before that noise was known in the systems. But what was surprising to him, when you look at the frequency spectrum, that is independent of the frequency. So that is not like 1 by f noise, and not only that, it does not depend on the temperature, so it is not also thermal noise. So he realized immediately that he has discovered something new, and it was called short effect. Later on it is like a famously known called short noise, and basically short noise can tells you that occurrence of large number of homogeneous elementary particles. So basically it tells you the discreteness of a quantum object. So that is the short noise can do it, and it is very important, for example, photon short noise, electron short noise, fractional charge in quantum Hall, fractional quantum Hall systems, and so on. And in the short noise, this the fluctuation, the way you characterize called the variance, and that is proportional to your mean current. Okay. So just to give a pictorial view what we do in experiment. So basically you can so what is happening. So imagine I have a train of electron which is coming, and you have a tunnel barrier, and tunnel barrier is very is really T is very small, T tends to much smaller than 1. So occasionally there is a 1 electron will tunnel through, and imagine I have a detector here, and it can measure the whenever electron goes through, you will measure a 1 coulomb charge. So whenever the these electrons are in the detector, you will see a spike, and this spike will happen randomly, because that is a completely random process happening, and this will create a noise. Just to contrary, imagine I have a transmission 1, then whatever the train of electron they will go through, and in the detector you will see a same pattern, there is no fluctuation, so you will not see anything. On the other hand, for example, imagine a scenario which is the case, because I will be talking about for Cooper pair. Instead of 1 electron, there is a if the 2 electron bonds together and they can tunnel together, and what will happen, occasionally there will 2 electron will come in a detector, so you will see 2 coulomb jump, and again 2 coulomb jump, and randomly will happen. Now you can immediately see the noise here, the variance will be higher compared to this. So this variance, the way we characterize, is called a Fano factor. So basically what it tells you, what we do in experiment, we measure the noise as a function of this current. At 0 current you have a background thermal noise, which is the equilibrium noise. As you increase this current, you have this short noise is created, and the slope tells you, basically tells you what is the Fano factor. For example, the single electron I was talking about, the Fano 1, which is called a Poissonian noise, so it will be 2 EI. So it will be your noise will be proportional to 2 EI, so Fano will be 1. In contrary, if you have 2 electron case like a Cooper pair, for example, then will be Fano will be double, like a Fano will be twice. So that's the exactly I am going to talk about. And these 2 values are universal values. However, it turns out that's true for the tunnel barrier, but in a mesoscopic device, our scenarios are much more complicated. And so what happens? There are lots of work by Nagev and later on Biniekar and so on, because they have lots of elastic scattering and so on. So Fanos are no longer now 1 or 2, but there are 2 other universal values one can have, and those values are called 1/3 and √3/4. In a decimal number, this is close to 0.33, and this is 0.43. So these are the 2 universal values, depending on electron length scale is smaller than channel length or so on, but these are the 2 universal values rather than 1 and 2 one can have. However, it turns out the question will be asking, which is very important to us, can I have a lower than this value? Can I have a noise lower than 0.33? It turns out from this spectrum, what you can see, if you have this regime when the length scale is very small in your system, which means the source and drain very small, there is no scattering. For example, ballistic regime. Ballistic regime, there is no scattering, so there is like a transmission 1, the picture I was showing in the previous slide, so there will be no noise. And indeed, the noise can suppress. There is another regime that when the length is too big, the electron phonon length scale kicks in and smaller than channel length, and you can show that the again noise can be suppressed. So these are the two regimes in a mesoscopic devices one noise can suppress. However, we will be asking question, is there any way beyond these two mechanisms the noise can be suppressed? And it turns out yes, there are theories and there are experiments. In fact, these theories are motivated by this experiment by this group, and they could, this is the only experiment available so far. They were measuring for this heavy fermion this system, which is a very well established the strange metallic phase, and they saw that for the gold they see like 0.33, the diffusive transfer what you expect, but for this noise was suppressed. It's much smaller than 0.33. So here the number is the most important. Again, I'll ask you to remember 0.33 and 0.43. These are the Fano factor, but smaller than that is very important, at least in this context. And they show the very very small Fano, and the idea is they say that this is the sort of signature of strange metal, because the way the way explained, they say that when you have a strange metal, so basically the quasi-particle description breaks down. So basically you can think it's sort of like there is no scattering. They don't feel this scattering in the system, and that's the way they explain that the noise is suppressed. Okay, so that's the thing I'm going to talk about, and let's bring to my experimental now what we have been doing. So we have reproduced now this result. There are lots of similarity, but there are subtle differences. But yeah, so there are two kind of devices, but mostly I'll consider second device. So the way these experiments are designed, so this is a magic angle twisted bilayer graphene. I have two gates. There is a local graphite gate and there is a called lead gates. So you can independently control the local density of my system. So for example, I can choose the whole system, everything is like a normal part. So normal, 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 or I can choose, here normal, superconductor normal, or I can choose the entire system is superconductor, or vice versa like SNS. So I have a full freedom to do the experiment in this system. So let's go to the response of these devices. So these are the resistance response of the sample. So this is the device 1 and device 2. So just to tell you what we see, typically if you have not seen the spectrum of magic angle twisted bilayer, so I told you this filling fraction plus minus 4. So this is the Dirac point, and if you increase, for example, conduction band, you see these are the correlated insulator peak, and this is the band insulator peak. But however, the superconductivity appear in the valency band. You can see there is a superconductivity appearing on this valency band, and the device 2 even, so here the TC was 0.5 Kelvin, but the device 2 is really an excellent device, and you see only I'm highlighting your valency band side. So this is the Dirac point as you go here. So this is your -2 filling the correlated insulator, but followed by you have a very strong superconductivity you have, and TC is of the order of 2 Kelvin. So now let's see, this is the RT diagram of the systems, and you can see this is the, I was talking about, this is the Dirac point, this is your Fermi liquid normal metallic part, this is your the correlated insulator. By the way, I have saturated the resistance here, and this is the superconductivity clean dome you can see. And so if you look at the cut, now I'll show you some of the cut line, you can see that for the Fermi liquid part, the resistance actually behave like a quadratic behavior, which is expected from the Fermi liquid, this part, these filling fractions. Now if you go to superconductivity, we know the resistance will go to 0, and that we see in this dome. And around that, if you kill the superconductivity by magnetic field, we see this sort of linear resistance even up to low temperature like 100 millikelvin. And so that, and just to compare the Fermi liquid hardly changes like in this part, but here the resistance changes much faster, around this superconductivity dome. And so that's initial indication the system is, which is well established, this, the strange metallic phase and so on. So now that's a noise measurement. So first experiment I'm going to talk about. So as I told you, I have freedom. I can put like, I can choose the thing. So let's do first, everything is normal. So this violet color, blue color, everything is normal part. So I can choose the gate 5 minutes. So I choose everything is normal part, and this is the noise data, the blue color. So this is the Fermi liquid part. I am measuring the noise, and if you feed the data, the slope is 0.33, which is expected, actually 0.32 or 0.3. So that is it's like a classic Fermi liquid, the noise Fano you look at. Interestingly, now if you switch the systems, these are normal, but make it this is the superconducting part. And as soon as you do that, now you see the noise, that this is your black data for the NSN junction, and you can see the noise Fano get a double. Instead of 0.33, 0.66 or 0.66. And most importantly, above the critical current, you see the noise is highly suppressed compared to the Fermi liquid part, and this is highly anomalous in nature. And this is the corresponding dBdi, Fermi liquid dBdi, you see as expected it's completely flat, the same data scale, just the resistance data. But if you look at the NSN junction, you see that critical current and followed by normal part. So there are two important messages in this slide. The Fano is double inside the critical current, and above the critical current, Fano is highly suppressed. Okay, so this is the more statistic, for various phases. So we can look at Fermi liquid phase for different points, and you see they are robust 0.33. And if you look at around the superconducting dome, they are doubled. So this is 0.6, and that tells you really the Cooper pair charge of 2e transport happening in the systems. And most importantly, if I analyze the above the critical current in the superconductivity phase, the Fano is highly suppressed, and that is the as I told you, this is highly anomalous. But however, this is in a highly non-equilibrium situation, because you are passing a very large current, and above critical current you have a suppressed one. So what we did now, of course, the immediate question is apply magnetic field, kill superconductivity, and see what happens. And this is the data now. So this is the increasing magnetic field, the noise I am showing. So this is a 50 millitesla, the 0.66 Fano I was talking about. And you can see that now as I increasing, so this is the above IC, the suppressed Fano you see. But the inner Fano decreasing now, because you are about to kill the superconductivity. And if you go down to 3 Tesla, it's hardly now any superconductivity is there. And you can see the Fano almost linearly increasing, and it's a very small, even very small current limit. And if I give you comparison, this is the 3 Tesla data in the superconductivity phase, killing the superconductivity, like a normal state of the superconductivity dome. This is the Fermi liquid part, which is hardly changing with the magnetic field. And we see that this is the large Fano 0.33, but here the Fano, even the small current regime, is 0.05. So highly suppressed. And if you do, okay, so that is the thing. And we have done not only single point, as a function of filling variations and so on. And this is the temperature dependence. Again, in the superconductivity phase, if you increase the temperature, this Fano doubling decreases, and above the TC, they becomes the Fano to the higher Fano values. And the most importantly, this suppressed Fano, what we see is independent of the temperature. So they are weakly dependent on the temperature. On the other hand, Fermi liquid Fano is highly dependent on the temperature. And that Fermi liquid Fano highly dependent, the monotonic decrement is expected in the theory using electron phonon coupling, but this is for the suppressed Fano is highly, this is again anomalous, the temperature behavior. And this thus brings us to summary of my slide. What I have done, we have measured basically the Fano, so as a function of current or magnetic field, but all at base temperature mostly, that 40 millikelvin. That is show that Fermi liquid phase, we see 0.33 Fano, that's the classic example. But in the superconductivity phase, inside the superconductivity phase, we see doubling of the Fano, but we kill the superconductivity, either critical current or magnetic field, we see highly suppressed Fano, and we believe this is probably the signature of strange metal, probably the strongest evidence so far what we have seen in the literature, and that brings us to whatever our collaborators and Sumil and Mohit, and there are lots of discussion and understanding and calculation using electron phonon coupling to understand what is going on, and these are the funding agency for the support. Thank you very much for your attention.
There are questions.
So it's very interesting. How does one understand this? Do we have any?
Oh, why suppression?
Yeah.
All experts are there. Sumilon, Rasdev, and Subir, and also Abiskar. There is a theory. Abiskar is he here? Abiskar is here. Yeah, Abiskar had a theory. There.
The words are that in the strange metal, there are no quasi-particles, so there is no discreteness to the motion of charge. It's much more.
Oh, I see. So
That's yeah. So is a
it's a fully entangled.
yeah.
Yeah, those are the words I'll use.
That's the reason I didn't answer. I would have done, but I said let's the experts make a comment.
Okay.
So at what frequency you generally do these measurements?
These are megahertz frequency. So that no 1 by f noise, all these things. Yeah, these are all LC resonance circuit and.
And when you are in the insulating state,
Insulating state we cannot measure.
But
So
you are
these.
measuring the phono all the way through.
No. Oh, that correlatory insulator we don't measure. So mostly metallic phase. Fermi liquid. Yeah. I mean these are all mostly metallic phase. I mean here and this superconductivity and this phase. This correlatory insulator we cannot measure. Yeah, of course. Yeah.
So you were seeing the suppressed pano when you are killing the superconductivity by increasing the current. Could you just kill it by temperature and see the low current? Or
Temperature, yeah, it's very good question. So the temperature problem is there's a other length scale, that electron phonon I was talking about, because even for, that's why the data I was, Fermi liquid also gets suppressed with temperatures. So this is the Fermi liquid, how it with the temperature behaves. Because the electron phonon kicks in and basically thermalizes and noise reduces. But you see the strange metal hardly depend on the temperature. In fact, this initial increment of train, I was looking at Abiskar paper, they also predict some sort of initial increment of this phase. Because you see there are okay, I don't know whether I'll, but there is a trend of increment rather than decrement this noise. Yeah.
resistivity is cleanly seen, the linear resistivity.
Yeah, but this temperature scale up to 2 Kelvin, that's the point, because there is a Lagrangian temperature effect or just strange metal. Because that's actually another point, because we are measuring everything as 40 millikelvin, so all at base temperature. Yeah.
Yep, over here.
Yes.
I'm mostly curious about how do you fabricate these samples? I mean, how great
So
you
students are
control
here.
over the twist angle, and is it uniform across the length of it?
Yeah. So actually, that's a very good question. So I mean, of course, the student, they know better than me, but it's very hard to hit the magic angle. The yield is, I think, last 5 years, maybe superconductivity, we have seen more than 5 samples out of maybe 50.
And is the twist angle? I mean, what is?
So that actually, that's how do you know this thing? Actually, that response of the device tells you many whether clean and this thing. And one thing I can point out, look at the fast device. I told you the TC is smaller, the TC is larger. This tells you one indications. Not only that you see the fast device at filling 2, you don't see the correlated insulator peak. And that is known because if you have a angle inhomogeneity and a metal and insulator and there is a percolating channel, then you will not see the insulator, but superconductivity is easy to see because it's a parallel path. But you see in this second device we see a clean correlatory insulator minus. So these are the signature, it tells you, I mean that's the only disorder. By the way, these are not the disorder by atoms or defects. Mostly the angle inhomogeneity disorder, but we believe this is one of the cleanest device what we have.
One last question. What is the distance between the source and drain height?
Yeah, so the actual device was measured around 15 micron. This second device, this is around 6 micron for this first device. Yeah. These are the 2 length scale we studied. Yeah.
Thank you.
So for this short noise measurement, you need a potential barrier, right?
So that's in a tunneling regime. So what I was talking mesoscopic device, so there is a scattering in the system itself, and that can create a noise.
From what scattering?
Like for example, elastic scattering, disorders, right?